AQA GCSE Physics Paper 2 revision video. So, welcome guys to another session. In this video, I'm going to be walking you through all the theory for all the topics that you're going to need to understand for the GCSE AQA Paper 2 exam, which is coming up. Alright, so if you don't know who I am, my name is Mr. Ceerazzledazzle. I'm a qualified physics teacher with over 15 years of teaching experience at some of the UK's state schools and leading independent schools, and I have an entire YouTube channel with a catalogue of videos to help you with your studies. I've got hundreds of stuff on there, so if you ever need any additional support, it's all going to be on there. Right, the reason why you should watch this video is it can obviously summarize everything that you need to know, all in one place. You don't have to look at other videos, and it's a nice thing to watch maybe before the exam. So let's say, for example, one day before the exam, you should watch this obviously to refresh your knowledge. And if you don't understand any of the topics or anything that I've said, or you are unsure about maybe like one aspect of it, if you comment below on the video, I respond to all the comments and I'll be able to help you on your educational journey. The topics being covered in paper 2 are going to be forces, waves, magnetism and electromagnetism, and space physics. All of it will be covered in this video, and therefore hopefully it solves all your queries that you have in the topic. The reason why I made this video is because I know that a lot of kids struggle in GCSE physics. It is a very hard subject, possibly one of the hardest out of all the GCSEs. So that's the reason why I made this, to hopefully clarify any misconceptions that you have and hopefully explain stuff in detail and in a fun and engaging way. If you're looking for videos to help you understand stuff in a bit more detail, then if you click on my YouTube channel, you can actually find I've got loads of playlists in which I've gone through every single topic in detail. So I explain it in a bit more depth. I do worked problems, and we spend a bit longer explaining certain concepts which are going to be much harder than actually watching just a revision video like this one. So make sure that you're ready to start. We're going to start in 3, 2, 1, let's do it. Right, so scalars and vectors. So there are two types of quantities. One of them is called a scalar and one of them is called a vector. A scalar has magnitude, which means size only, and a vector quantity has magnitude and direction. So it has a size and direction. Vector quantities can be negative and they have a direction, and that direction can be represented using arrows. Some examples of scalar quantities are going to be speed, distance, time and mass. They only have a value, they don't have a direction. Examples of vector quantities can be the velocity, displacement, force and acceleration. Don't forget force, it can be represented with an arrow, yes, for the direction. So all of these can be vector quantities. Contact and non-contact forces. So contact force, objects which are physically touching each other, and non-contact forces are going to be objects which are not physically touching each other. Some examples of contact forces are friction, air resistance, tension, normal contact force. So like friction, two things rubbing together, air resistance, you're traveling through the air, tension when you're pulling things, and normal contact force when you place an object, let's say on the surface, the force pushing upwards over here. Non-contact forces can be gravitational force, yes, the way of gravity, let's say a moon's being attracted by a planet, yes, they're not touching, but there's a force between them. Electrostatic, so two charged particles, let's say one's positive and that one's positive, there's a force between them. Magnetic force, don't forget, if you have a north pole next to another north pole, they will both repel each other, so these are all non-contact forces. Weight, mass and gravity. So first of all, mass and weight are not the same. Mass is the measure of how much matter an object has, and it's measured in kilograms. The weight is a force, and therefore it is measured in newtons. Your mass is the same wherever you are in the universe, so your mass will remain the same, but your weight will change depending on the strength of the gravitational field of that planet. In order to calculate the weight of an object, it's simply going to be the formula: weight is equal to mass times by gravitational field strength. W is equal to m times by g. Weight is measured in newtons because it's a force, mass in kilograms, and the gravitational field strength will be Newton per kilogram. And over here you can see I've got an object over here, and the weight's acting downwards right through the center. The weight acts along the line of action drawn from the center of mass of the object. That simply means that the weight is going to act downwards from the center of the object over here. The center of mass. So the center of mass is simply going to be the point at which all the mass appears to act. So if I give you this square, we can quickly find it by going along the axis of symmetry over here and over there. As you can see, they cross, and therefore the center of mass is going to be right bang in the middle over here. So for this one, it's over there, and if this one, you can see it crosses, so the center of mass will be in this point over here. So when you find the lines of symmetry where they all intersect, that's where the center of mass can be found. Resultant forces. Resultant forces is simply going to be the overall force acting upon an object. So over here, as you can see, I've got an object over here, this ball, and there are all these forces acting on it. Well, look, we've got 10 newtons to the left, 10 newtons to the right, 30 up, 30 down. Well, the horizontal ones will cancel out and the top and bottom ones will leave a resultant or overall force of 20 newtons upwards over here. 30 minus 10, it's 20 upwards over here. And don't forget, forces, the length of the arrow indicates the size of the force. That's why the 30 Newton one is much larger than the 10 Newton one. Parallelogram of forces. So let's say we have two forces acting upon an object. Yeah, I usually try and explain it with like a dog, and there's two leads attached to the dog. And if you're asked to work out what is the resultant force upon the object if it's being pulled in two directions, you've got to construct the parallelogram of forces. So first of all, you take both of the forces and you shift one downwards over there. So this force goes down over here. The other force goes across over here. And then all you do is simply drop a line from one end all the way to the opposite end of the parallelogram over here. When you're doing this, you actually have to draw it to scale. So the length of this arrow must be of a certain size. And the size obviously indicates the value of the force. So when you're drawing it, you must use a scale diagram. It could be 1 centimeter represents 1 Newton. That is a suitable scale. Or maybe 1 centimeter represents 2 Newtons over here. So when you're drawing this, once you've done this, you've constructed the parallelogram, then you've drawn the resultant force in between. Yes, then you measure the length of the resultant force. And then from here, you can work out the value of the resultant force, obviously using your scale. And you may be asked for the direction. You simply have to measure the angle with a protractor and also quote it. Resolving forces. Resolving forces simply means splitting up forces into separate components. So let's say I've got a 5 Newton force over here and it's drawn to scale, 30 degrees to the horizontal. If you're asked to resolve this, basically that means that you're going to split it into horizontal and vertical components. So over here, basically, you're going to use a scale diagram. Yes, don't use trigonometry, just draw a scale diagram. You simply drop a line across and drop a line upwards, and then you measure the length of the line, and using your scale, work out the value of the force. So there we go, we have now resolved this force of 5 newtons vertically and horizontally over here. So don't use Pythagoras or trigonometry when you're doing this, simply use the scale diagram. Resolving forces on the plane. Right, so let's say we have the object and it's now on a slant. Yes, it's on a slanted plane over here. If you're asked to resolve the force, which is pulling it down right now, which is 5 newtons, you now need to resolve this parallel and perpendicular to the plane. So basically, if I was you, I'd say construct a triangle over here. So look, we've constructed this triangle and we can see that now, and don't forget the triangle is right angle triangle over here. This force pulling downwards is now, look, parallel to the plane, and this force over here is going to be perpendicular to the plane over here. So once you've constructed your right angle triangle, you're simply going to measure the length of this arrow and obviously use your scale to work out how much that force would be. And you do the same for the parallel component. So that's how you resolve forces on a plane. You do it parallel and perpendicular to the plane. Work done. The work done is simply going to be the energy transferred via forces. So work done is equal to force times by the distance moved along the line of action of the force. That simply means that if I have a force acting in this direction, I'm looking at the distance in that same direction. So work done, W, is equal to F times by S over here. Work done is energy, therefore it's going to be measured in joules. The force is in newtons, capital N, and the distance is in meters over here. And look, on the right hand side, I've got a simple calculation which you can pause the video and obviously go through it yourself. Power. Power is equal to the rate at which energy is transferred. Power is measured in watts. Yes, power is measured in watts. Power is equal to energy transferred divided by time taken, and therefore P is equal to E over T. That's the formula. Power is measured in watts, energy is in joules, time is in seconds. So make sure you get the correct units down. Also, you should remember that energy transferred is the same as the work done, so therefore power is also equal to work done over time. So power is equal to W over T, where power is in watts, the work done is a measure of energy, therefore joules, and the time is in seconds. And on the right hand side over here, you can see I've got another example. The relationship between force and extension of a spring. Right, so this is a simple practical that you should be aware of. So imagine I have a spring of length L, and we're going to look at how the extension of the spring changes as you add masses to the end of it. So when you add a mass to the end of it, first of all, it will have a final length F. To work out the extension, you do F minus L, that will tell you the extension, how much it is extended by. Then you would keep adding masses at the end of it. Obviously, it would extend more and more. So look at my table of results. First of all, I have the original length L, and then we're going to add the mass over here. Final length F. Therefore, to work out the extension, I'm going to do the final length minus the initial length that goes in this column over here. Then the force. Don't forget, I don't want to talk about the mass, I want to talk about the force. The force is simply the weight of the masses at the end, which is going to be mass times by gravity. That's this one over here. Then you repeat this, keep adding masses each time here, taking all your values. Control variables, use the same spring throughout the experiment. Risk assessment, wear goggles in case the spring bounces off and causes eye injury. And obviously don't put your feet underneath the masses. Errors, when taking measurements of the length, ensure that you are eye level with it, so therefore you reduce the parallax error. And then you should get the following graph of force versus extension. It should be going up initially. It may curve off at the end, but you should go up first of all and then curve off at the end. Force extension graph. So there are parts of the force extension graph you should be familiar with. The first one's going to be the limit of proportionality. I always call it LOP. It's the last point at which the force is directly proportional to the extension over here. The elastic limit is after the limit of proportionality. This is the point at which the spring, if you go beyond this point, it will not return back to its original length. But if you're up to that point, it will return back. So beyond the elastic limit, the spring will now become deformed. Before it, obviously the spring will return back to its original length. And then if you keep on adding masses, what happens is that eventually you'll reach the breaking point, which is going to be BP. We can call the left-hand side here, this region over here, the elastic behavior, and the right-hand side going to be the inelastic behavior, sometimes called the plastic behavior as well. Hooke's law. Right, so up to the limit of proportionality, we should recognize that force is directly proportional to the extension. Therefore, the force is proportional to the extension over here. Therefore, F is equal to a constant times by E. We're going to call this constant K, and that represents the spring constant. It's a measure of how stiff the spring is. The greater the spring constant, the stiffer the spring is. So looking at this, force is in newtons, extension in meters. The spring constant is Newton per meter over here. And look, if we're given the graph of force versus extension, if I was to work out the gradient, it's the change in y of the change in x. It's the change in force divided by the extension, which is going to be the spring constant K. The elastic potential energy. So the elastic potential energy is stored in the spring. So if I was to add masses to it, hopefully you recognize it would have energy stored. What would happen is that we can work out the elastic potential energy using the following formula. It will be half times by the spring constant times by the extension squared. So there we go. E is equal to half KE squared, where E is in joules, the spring constant is still in newtons per meter, and extension is going to be in meters. Levers. So this is basically going to be the physics behind how a spanner works or how a wheelbarrow works. So look over here, we have a wheelbarrow, we've got a load on one side and effort on the opposite side. We've got a pivot point over here. The pivot point is where it rotates about. Right, so first of all, recognize that the greater the distance from the pivot, yes, the greater the force on the load. So obviously if I push from down below, I'll have less of a force on the load. So as I increase the distance from the pivot, the greater the force will be on the load to lift it up over here. And look, on this side over here, we have a seesaw. So look, on one side, I've put a load, it's pulling it down. But obviously to balance it out, I must push down the effort on the opposite side. And as you can see, because the effort is a greater distance from the pivot, obviously it has a bigger effect on the load. Levers are force multipliers, which means that they can produce a greater output force than the effort force applied. So therefore you might have a small amount of force there, but you can get a bigger force because your distance is greater. Moment. A moment is simply a turning force. The moment is equal to the force times by the perpendicular distance from the pivot. So over here we've got a pivot point and this is our beam. Moment is equal to force times by the perpendicular distance. Therefore force is in newtons, the distance is in meters, and therefore the moment is in Newton meter. Moments can either be clockwise or anti-clockwise. So in this case over here, we know it's going to spin the beam anti-clockwise. It's trying to drag it anti-clockwise over here, therefore causing the beam to turn. The principle of moments. So for any beam to be balanced, we need to have the following rule. The sum of the anti-clockwise moments must be equal to the sum of the clockwise moments. So that simply means that, look, in this example, we've got A, B, and C, 3 different loads on the seesaw. We can recognize that the moment of the anti-clockwise ones, which is the A, yes, that's anti-clockwise, trying to pull it anti-clockwise, will be equal to the moment of B plus the moment of C. There we go over here. So the moment of A is equal to the moment of B plus the moment of C. Therefore, F1 times by D1 is equal to F2 times by D2 plus F3 times by D3 over here. And therefore, this proves that the beam is balanced. Pressure. Pressure is simply going to be the force acting per unit area. P is equal to F divided by A, and that's going to be the area in contact with the table. Yes, let's say we have this box, the area in contact with the table, that's the force pulling down over here, that's my arrow. In terms of the units, the force is in newtons, the area is in meters squared. The pressure will be measured in Pascal, but don't forget 1 Pascal is the same as 1 Newton per meter squared. Gas pressure, so we've talked about this in the kinetic theory video, which I've done previously, but we'll just revisit it again because obviously it's about forces. So number 1, particles inside a gas, they travel across, they collide with the walls of the container. Each collision they exert a force. Because there is force acting per unit area, which is the walls over here, therefore there is a pressure. There is now a pressure over here. The pressure in a fluid, so right now the pressure in a fluid, to work out the pressure in the fluid, it's equal to the density of the fluid times by the gravitational field strength of the planet that you're on times by the height of the fluid. P is equal to rho GH, where P is the pressure in Pascal, density is in kilogram per meter cubed, gravitational field strength is Newton per kilogram, and H is the height over here, which is measured in meters. That means the height from the top of the surface downwards, so that is going to be H in this diagram here. Atmospheric pressure, so here is the Earth's surface, and look, the air above the Earth's surface, usually we think about it as uniform density, yes, equally spaced, but in reality it's not. Gravity acts on all the particles and it drags those particles down to the surface of the Earth over here. So therefore, as the altitude increases, as you get further and further up, the pressure decreases. And then we get the following graph, that pressure versus altitude. We can see that as the altitude increases, the pressure drops down. So the pressure is going to drop down. Because we're talking about a fluid still, we can still use the formula pressure is equal to density of the fluid times by the gravitational field strength times by the height of the fluid over here to do calculations about atmospheric pressure. Distance versus displacement. So now, distance versus displacement, so this is going to be scalars versus vectors one more time. So over here we've got an object A and it's trying to get to B. So first of all it moves 5 meters up, 6 meters, 4 meters and 9 meters. Total distance is an addition of them all, 24 meters. The displacement is simply the direct route from A to B over here. There we go, and measuring that distance over here. Obviously, because it's a vector, we're going to have to put the angle theta. So distance is going to be a scalar quantity and displacement is going to be a vector quantity because look, it does have a size and it now has a direction. The basics of motion. So first of all, you should hopefully identify that speed is equal to distance divided by time. Yeah, the speed of an object is going to be the distance divided by time. That's a scalar quantity. Velocity is the vector version. It's the displacement divided by the time. So we can have the following. V is going to be the velocity. Displacement is S. Time is in T over here. And look, velocity is going to be measured in meters per second because you're dividing the meters of a displacement divided by time in seconds. That's why it's meters per second. Couple of things you should be aware of is that the average walking speed is 1.5 meters per second, running 3 meters per second, and cycling 6 meters per second. The speed of sound is also 330 meters per second. Just make sure you're familiar with those values. Now, distance time graph. So over here we have a distance time graph. On the y-axis, I've put the distance, x-axis, I've put the time. Hopefully you can recognize that if it's a diagonal line, it means it's a constant speed. If it's a straight horizontal line, it means it's stationary over here. If I wanted to work out the speed, it's simply going to be the gradient of the diagonal line because it's the change in y over the change in x. And don't forget, on the y-axis, you're changing distance divided by time taken. Distance divided by time is going to be the speed over here. So just summarizing that, the gradient of a distance time graph represents the speed, and the higher the gradient, the greater the speed. Acceleration is simply the rate of change of velocity. So there we go, acceleration is equal to your change in velocity divided by time taken. That's the same as your final velocity minus your initial velocity divided by the time taken. And acceleration is a vector quantity, so it can have a size and direction. If it is positive, that means you're accelerating, you're gaining velocity. If it's negative, you're going to be losing velocity, therefore it's called deceleration. Right, so our formula is going to be A is equal to delta V divided by T. Acceleration is equal to delta V over T, and A is therefore equal to V minus U divided by T. In terms of the units, the top line over here is velocity because it's final velocity minus initial, it's still velocity, meters per second divided by second is the same as meters per second squared. And we have another formula which is going to be V squared is equal to U squared plus the 2AS. Make sure you're able to use that and rearrange that to make V the subject or U the subject, where V is going to be the final velocity, U is going to be the initial velocity, A is going to be the acceleration, and S is going to be the displacement. Velocity time graph. So right now I have a velocity time graph over here. First of all, we can see that if it's a diagonal line going upwards, you are accelerating because you are changing velocity. If it is a straight horizontal line, it's a constant velocity over here. And if it's going down, it's going to be deceleration going downwards. If I was to look at the gradient of this line, because the gradient of the line is the change in y over the change in x, it's the change in my velocity divided by change in time, which is the acceleration from before. So the gradient of a velocity time graph represents the acceleration. The higher the gradient, the greater the acceleration. So the higher the gradient of that line, the greater the acceleration. Okay, and also if I'm asked about the distance travelled for this journey, it is simply going to be the area under the line. So the area of a velocity time graph represents the distance travelled over here. You can either use the trapezium rule for the area, the half a plus b times by h to do that, where this is a, this is b, and the h is the distance between them. Or you can work out the area of this triangle plus the area of this square plus the area of this triangle over here and add them together to work out the total distance. Non-uniform motion. Let's say you're given a distance time graph and the graph is curved and you're asked to work out the velocity. Right, you can't do the gradient of the line because it's not straight, but you can use the tangent rule. So the point you're looking at, let's say you're looking at the time of this time over here, you start to construct a tangent at this point and then you work out the gradient of the tangent. So there we go, as you can see I've constructed a triangle and now I'm going to work out the gradient of this triangle. So the gradient of this tangent on the displacement time graph, it represents the velocity. So make sure that you're happy with that. So I can use the gradient of the tangent to work out the velocity from a non-uniform displacement time graph. Also, if I'm given a velocity time graph of non-uniform motion, look, the graph is curved, and I'm asked about the acceleration, I simply have to do the tangent rule again. So we construct the tangent over here, and once again, we'd use the gradient of the line because the gradient of the tangent on the velocity time graph will represent the acceleration because you're having the change in velocity divided by the change in time. Terminal velocity, let's talk about the forces acting upon a skydiver when they jump out of a plane. So initially the only force acting upon it is the weight pulling it down and therefore the object accelerates. But as it falls down through the air, what happens is air resistance starts to build up. Yes, so the acceleration starts to reduce. It's still moving downwards, then eventually the air resistance balances out the weight. So when the two forces are balanced, what happens is the object will no longer accelerate, it will move off at a constant velocity. And this, the final velocity it reached, this is called the terminal velocity because it's the final velocity it reached over here. Then when the skydiver opens up the parachute, what happens is the air resistance increases dramatically. So the air resistance increases dramatically and therefore the object starts to decelerate. You start to decelerate. And then finally, the two forces balance out again, and therefore the object starts to travel at a lower constant velocity. So yes, it's a lower terminal velocity at the end. Let's look at it in terms of a graph. So over here, guys, you can see that, look, we've got a velocity time graph. So initially, yes, the weight is acting and it accelerates, but as the air resistance builds up, the acceleration starts to decrease, hence why the graph is starting to level off. Then at terminal velocity, don't forget the velocity is not changing, that's why it's flat. And then finally, when you open up the parachute, we decelerate, and then eventually the forces balance out again with that lower terminal velocity over here. There we go, and finally you hit the ground. Newton's first law. Newton's first law states the following, that if the resultant force upon an object is zero, that means that the forces are balanced, the object will either remain stationary, yes, or move at a constant velocity. So over here, look, if the two forces are balanced, it's stationary. Two forces are balanced here, up and down are balanced, it's stationary. But we also just looked at when the two forces are balanced and it's still moving. But don't forget, it's moving at a constant velocity. So this is going to be Newton's first law. Newton's second law. Newton's second law states that if there is a resultant force upon an object, well, the object will accelerate. So look over here, we've got an object and it's got all these forces acting upon it. Hopefully you recognize that the resultant force is 80 newtons upwards. 100 minus 20, 80. Yeah, 50-50 cancel out. Newton's second law states that the acceleration is directly proportional to the resultant force acting upon it, provided that the mass is constant. And it also states that the acceleration of the object is inversely proportional to the mass of the object. So therefore, the greater the mass of the object, the lower the acceleration will be. So we have F is proportional to A and A is proportional to 1 over m. Combining them together, we get the resultant force, which is this symbol, sigma. F is equal to m times by A, where the force is measured in newtons, the mass is in kilograms, and acceleration is meters per second squared. Investigating the effect of varying the force on the acceleration of an object for constant mass. Okay, so this is quite a tricky experiment, but I'll walk you through it. Over here we have a trolley and it has a piece of string attached to it and it's hanging off the edge of a table on a pulley, and look, it's attached to some masses at the bottom over here. So what we're going to do is the following. We're going to take masses from the top of the car and place them at the end over here, and we're going to see how it accelerates through here. Right, we're looking at how the force pulling down, don't forget the force which is pulling down will be the same as the force pulling across, and how that affects the acceleration. We're going to keep the mass of the entire system constant by taking masses from the top of the car and placing them over here. That's how we're going to keep the mass constant. Right, so what is the data logger? The data logger is going to take some measurements for us. The data logger is connected to the light gate 1 and light gate 2 over here. As the car accelerates and goes across, it will go through the first light gate over here. As it goes through the first light gate, what will happen is the data logger will therefore calculate the initial velocity. That will go into our table over here. Then as it goes through the second one, it will calculate our final velocity. Right, how are you going to work out the acceleration? You're going to also time how long it takes to move between this light gate and this one using a stopwatch. So therefore we can get the final velocity, initial velocity and time taken. We can work out acceleration as the change in velocity divided by time. How are you going to get the force? That's simply going to be mass times by gravity over here. And look, we've got our control variables. Keep the mass of the system constant by taking masses off the trolley and place them at the end of the mass hanger. The risk assessment is obviously don't put your feet under it. So therefore from here we can get the following graph. Force versus acceleration. We can hopefully see that the greater the resultant force, the greater the force acting on the end of the pulley, the greater the acceleration on the car. Second experiment, investigating the effect of varying the mass of an object on the acceleration produced by a constant force this time. So this one is slightly different. In the previous example, we were taking masses off and adding them to the end, therefore increasing the force. This time round, I'm going to keep the force the same, so I'm not going to change any masses at the end. So what we're going to do is we're going to take additional masses and simply add them on top here. So masses are added here only. They're not taken from anywhere else. So once again, you're going to add masses to the trolley over here and release it. Hopefully you will recognize that we're going to measure the initial velocity one more time, final velocity, time in between, and work at the acceleration. And the more and more mass you add on here, obviously if this force remains the same, therefore the acceleration would decrease. So the greater the mass on the trolley over here, the lower the acceleration should be. And the control variables in this experiment have slightly changed. We're going to keep the mass at the end of the hanger constant. The reason why is because we need a constant force pulling it downwards. In terms of the results, what should you obtain? You should obtain the following graph, that as you increase the total mass of the car, the more and more mass you add on top of the car, the acceleration would decrease. Don't forget, they are inversely proportional to one another. Yes, because A is proportional to 1 over m. Inertia. Inertia is the tendency of an object to remain in its existing state. So for example, if an object is at rest, it would like to remain at rest. If the object is moving at a constant velocity, it will want to remain at a constant velocity. All objects have inertia, moving or not. So there we go, we've got a stationary object. Yeah, inertia wants it to remain, not moving. And look, an object moving at constant velocity, it wants to remain moving at constant velocity. The inertial mass is simply a measure of how difficult it is to change the velocity of an object. The greater the inertial mass, the harder it is to change its velocity. The lower the inertial mass, the easier it is to change its velocity. To calculate the inertial mass of an object, we simply look at the ratio of the force over the acceleration. So m is equal to F divided by a, which is from Newton's second law. Newton's third law. Newton's third law states that forces exist in pairs, and if object A exerts a force on object B, then object B will exert an equal and opposite force upon object A. Here are two examples. So over here we've got an object that's resting on a surface, therefore the weight of the car pulling down is equal to the normal reaction force pushing upwards. They're both balanced out. And here's a non-contact example. So as you can see, we can see that the Earth attracts the moon, but also the moon attracts the Earth as well. Yes, that's the reason why we have the tides. They're being pulled closer towards the moon. Stopping distance. Stopping distance is the total distance traveled by the car, which is equal to the thinking distance plus the braking distance. Thinking distance. The thinking distance is the distance traveled by the car from the moment you spot the hazard until you apply the brakes. Don't forget, as you're thinking about it, applying the brakes, the car is still moving. It is affected by our reaction time and the speed at which you're traveling at. The braking distance is the distance traveled by the car once the brakes have been applied. The braking distance is affected by physical factors, not like the thinking distance. Over here, I have a simple diagram in which a car is moving, then comes to a stop over here. So initially, there's the distance traveled is going to be the thinking distance, the brakes are applied, and then it's the braking distance from here. But the total stopping distance is the addition of the thinking distance plus the braking distance as stated above. Factors affecting thinking and braking distance. Right, so these are the factors affecting the thinking distance, which is going to be alcohol consumption, intoxication of drugs, age, mental health, distraction, tiredness. Factors affecting the braking distance are going to be the condition of the tyres, condition of the brakes, friction of the road, and weather conditions. So look, all these ones are more physical. These ones are about the human reaction time. And over here, what is going to be the intersection? Speed is affecting both your thinking distance and your braking distance. So the faster you are, the greater your thinking distance and braking distance will be. Momentum. Momentum is simply how difficult it is to stop a moving object. Momentum is a vector quantity, therefore it has a size and direction. It can have a negative value. The negative value indicates the direction. Right, so momentum, the formula is equal to the mass of it times by the velocity. There we go, P is equal to mv. Mass is in kilograms, velocity is in meters per second, therefore the momentum is in kilogram meters per second. Over here we can work out the momentum of this to be 60 kilogram meters per second, but because I've taken going to the right as positive, going backwards this direction, it has to be negative. So look, the momentum of this one will be minus 120 kilogram meters per second because it's moving in the opposite direction. The principle of conservation of momentum. The principle of conservation of momentum simply states that the sum of the momentum before the collision is equal to the sum of the momentum after the collision. So that means all the momentum before should be equal to all the momentum afterwards. I'm going to walk you through multiple examples so that you can get your head around it. So in this example, I've got car A colliding with car B. Car B is stationary. But afterwards, when they collide, they stick together and they move off. Well, hopefully you can see that the sum of the momentum before is equal to the sum of the momentum afterwards. So the momentum of this plus momentum of this one should be equal to the momentum of both of them combined together afterwards. And look, if you check the maths, 20 times by 3 over here plus the 5 times by 0 should be equal to 25 times by the 2.4. It's 60 on both of them. Yes, momentum is conserved in this example. Alright, so this one is going to be a collide and separate scenario. So look, this one is going to be car A collides with B, but they don't stick together. They just keep on moving. So this is the before the collision, this is afterwards. So once again, the sum of the momentum before is equal to the sum of the momentum afterwards. So that means that the momentum of A over here plus momentum of B will be equal to the momentum of A over here plus this momentum B afterwards. So therefore it goes 20 times by 3 plus 5 times by 0 will be equal to 20 times by 1.5 plus 5 times by 6 over here, 60, 60, and look, momentum is conserved. Obviously they're all in the same direction, that's why all the values of the velocity are positive. Another example of the principle of conservation of momentum is going to be a collide and stop scenario. That means that two objects collide together and they simply stop moving. Well, look over here, we can say that sum of the momentum before the collision must be equal to the sum of the momentum after the collision. So here's before and afterwards. So therefore we can say momentum of A plus momentum of B must be equal to the momentum of this afterwards. Well, we know that it's not moving afterwards, so therefore the momentum of it afterwards is going to be 0 on the right hand side. The momentum of this one is 20 times by 3 plus 5 times by minus 8. Careful, but it's negative because obviously it's moving in the opposite direction. So therefore 40 minus 40, yes, it's 0 on both sides, and this is another example of the conservation of momentum still working. Last example of the conservation of momentum, this is going to be a cannon and cannonball explosion example. This is the one I always try and use to explain it. Let's say we have a cannon over here, A, and B is the cannonball inside. Initially it's not moving, then afterwards the cannonball flies off over here and the cannon moves backwards right now. So therefore we can still do the same thing. The sum of the momentum before the collision should be equal to the sum of the momentum after the collision. So the momentum of this before must be equal to the momentum of this afterwards. So initially it's not moving, so therefore the momentum on the left hand side is going to be 0, but on the right hand side I've got 20 times by 1, yes, plus 5 times by minus 4, yes, which therefore 20 minus 20, they both cancel out, and therefore the principle of conservation of momentum still works. Elastic and inelastic collisions. So in elastic collision, what happens is the momentum is conserved and the kinetic energy is conserved. In an inelastic collision, only the momentum is conserved and the kinetic energy is not conserved. The rate of change of momentum. So over here, let's say we have a bus of 20 kilograms and it's traveling and it comes to a stop over here. Let's say it comes to a stop in 2 seconds. We have another bus of the same mass at the same initial speed and it comes to a stop in 100 seconds. In which scenario would you experience the greatest amount of force if you were inside the bus? Well, hopefully you recognize that it's going to be in the first one. Why? Because you change momentum in the shortest amount of time. So the rate of change of momentum affects the force experienced. So the shorter the time, the higher the force experienced for the same change in momentum. And the longer the time, the lower the force experienced for the same change in momentum over here. So now let's derive a formula for the rate of change of momentum. First of all, we should remember that Newton's second law, F is equal to ma. The acceleration is the change of velocity divided by time taken. We can plug that in, which is equal to mv minus mu, because don't forget v is final velocity minus initial. Therefore, the force is equal to the final momentum minus the initial momentum, and we can therefore say this is the change in momentum divided by the time taken. So yes, force is equal to the change in momentum divided by time taken, and if we look at the graph of force versus time, we can see they're inversely proportional to each other. And airbags, crumple zones, cycle helmets, cushion surfaces on playgrounds all use this principle. They all increase the time of the collision to reduce the force experienced for the same change in momentum. Gears. A gear is a toothed wheel that rotates about their midpoint. So look, we've got two gears, they're round, they've got loads of teeth around them. And look, the small one is connected to the large one over here. We can see that as the small one rotates clockwise, the other one rotates anti-clockwise right now. The key thing to notice about the gears is that the force they have acting on each other is going to be the same, but they have different moments. Don't forget, both of them are turning, so they have turning forces. They will have moments within them. So we can then say that the force from gear 1 is equal to the force from gear 2. If you're wondering where the distance is in this, it's going to be the radius of the gear right now. So this is going to be D1, this is going to be D2 over here. We also should remember that a moment is equal to force times by distance, so therefore force is moment divided by the distance. So I can replace the force acting on the first gear is equal to M1 over D1, and the force acting on the second gear is equal to M2 divided by D2. Then just summarizing it all, that a small gear driving a large gear, let's say I have a small gear driving a large one, the small gear is going to rotate faster because it's smaller, it's going to be easier for it to make a complete circle compared to this one. The large gear is going to rotate slower. If the small gear turns anti-clockwise, the other gear turns clockwise. This one will have a smaller moment because it has a smaller radius, this one will have a larger moment produced. If we have a large gear driving a small gear, we notice that the large gear will rotate slower than the smaller output one. If the large one is going to rotate anti-clockwise, the smaller one will rotate clockwise. And you have a larger moment input and a smaller moment being produced from the smaller gear. Transverse waves. Transverse waves, the oscillations are perpendicular to the direction of energy transfer. Longitudinal waves, the oscillations are parallel to the direction of energy transfer. Here's a diagram of a transverse wave. The wavelength is going to be from one point in a wave cycle to its next identical point. So from peak to peak or trough to trough. The symbol is going to be the Greek letter lambda, which is going to be the symbol over here. It looks like an upside down inverted Y. And the amplitude is going to be from the peak to the rest position. So the rest position to the peak is going to be the amplitude. Amplitude and loudness. So over here we have two diagrams. We can see that there's a relationship between the amplitude of a wave and the loudness. The greater the amplitude of a wave, the louder the sound will be. Notice they have the same frequency, but we can see that this sound on the right hand side is going to have be much louder than the previous one. Reason why is because the amplitude is going to be higher. Longitudinal waves. So longitudinal waves, here we go. First of all, recognize that longitudinal waves have compression. So imagine I have a slinky spring and we shoved it one side. We know that the springs will bunch up at certain points and they'd be separated out at other points. The points where they bunch up together is going to be called the compression. The points which they are further away is going to be the rarefaction over here. The distance between one compression, the center of it, to the next compression is going to be called the wavelength, or the distance from one rarefaction to the next one over here, that can also be the wavelength. Sound waves. So sound waves are longitudinal waves. Here is a speaker. Let's say this is yourself. This is the air undisturbed in front of you. When a sound wave tries to travel, what happens is obviously compressions get set up. So the air particles, they are disturbed. They bunch up at points called compressions over here. So look, they bunch up compressions. There's a rarefaction, there's a compression over here. And therefore, the wavelength in this will be from one compression of air particles to the next one. So sound waves are longitudinal waves. Determining the speed of sound. If you want to determine the speed of sound, simply you take two bricks over here, you hit them together, and you see how the sound wave travels, hits the wall and bounces back. Yes, so the sound wave goes forward and travels back over here. In order to work out the distance, you simply measure the distance between yourself and the wall. So the distance between that going there, yes, and then you're going to time the time taken for you to hear the initial sound and for the echo to return. So don't forget, you're listening out when the sound returns over here. The distance, what about the total distance traveled? Don't forget, if you want to work out the speed, speed is equal to distance divided by time. The distance will be the distance there and back again. So you multiply this the value that you measure over here by 2, and that's how you can then use that to work out the speed of sound. Yes, because the speed will be equal to the total distance traveled divided by time taken. Frequency. Frequency is going to be a measure of how many waves there are per second. It is measured in hertz, capital H, little z. Yes. The higher the frequency of a sound wave, the higher the pitch. That's going to be the key thing. So if you have a high pitch sound, the frequency will be higher. Over here, we've got a formula. The frequency is equal to the number of waves divided by a total time. And look, we've got two diagrams over here. The first one, we've got 2 waves occurring in 10 seconds. And this one, we've got 1, 2, 3, 4 waves in 10 seconds. So this one is a low frequency. This one is a high frequency. Frequency is the number of waves divided by total time. So look, we've got 2 divided by 10. The frequency for the first one is 0.2 hertz. For the second one, it is 4 divided by 10. So it's 0.4 hertz over here. So obviously, the greater number of waves you have per second, the higher the frequency. The time period is simply going to be the time taken for one wave to occur. So as you can see over here, let's say we've got this diagram. We've got 2 waves occurring in 10 seconds. What is the time period? Yeah, what is the time taken for one wave to occur? Well, it'll be 5. Yes, 5 seconds over here. So the time taken for one wave to occur. The frequency of this is 0.2 because you've got 2 waves divided by 10 seconds. Don't forget, total number of waves divided by time. So 2 divided by 10, it will be 0.2. And the time period is 5. There is then a formula which links the frequency and the time period. The frequency is equal to 1 divided by the time period. Hopefully you can see that with regards to the mathematics over here. So frequency is equal to 1 over t. Frequency and wavelength. So right now I've got 2 diagrams, one on the left hand side and one on the right hand side. We can see that this one has a low frequency, but it's got a very long wavelength. The distance between peak to peak is much larger. But look on the right hand side, we've got a very high frequency. There are more waves per second, but the wavelength is shorter. So we can see that if you have a low frequency, you're going to have a long wavelength. And if you have a high frequency, you're going to have a short wavelength. This leads us to the wave speed equation. That's the wave speed. To calculate the speed of a wave, it's equal to the frequency times by the wavelength. V is equal to F lambda. Look at the units. Velocity is meters per second, frequency is in hertz, and lambda is going to be measured in meters. Make sure that you are familiar with those units. Ultrasound waves. Ultrasound waves are going to be, first of all, any sound wave which is greater than 20,000 hertz. So this is our human frequency range, 20 hertz to 20,000 hertz. Ultrasound will be greater than that amount over here. So ultrasound is going to be used in the imaging of unborn fetuses, detecting cracks in solid objects, sonar when they measure the depth of the sea floor, ultrasonic cleaning, and the breakdown of kidney stones. They are also non-ionizing, therefore they are safe to use on the human body. Ultrasound images. Okay, so here's a very simplified diagram of this. There's a person, yes, a pregnant woman, and what happens is you've got the ultrasound transmitter over here. You put some gel to allow the maximum absorption of the ultrasound waves. They're going to travel outwards, hit the fetus, and the wave bounces back. So a live image is obtained. Ultrasound waves are non-ionizing, therefore there is no risk to the mother. Sonar. So look at the word sonar. It's sound navigational ranging. Yes, and look, that's why we got SONAR over here. So the boat sends out an ultrasound wave of a known speed to the bottom, yes, and it reflects and bounces back up over here. So you time the echo once again. So in order for you to work out the distance from the boat to the seabed, they're going to use the formula half V times by T. Why do I need to half it? Because don't forget, this is the time of the echo, is the time taken for it to go there and back again. So therefore, I only need half the distance. That's why I need to half it overall. So just make sure you're happy with that. Detecting cracks in solid objects. So let's say, for example, we have a solid block over here and there's a crack inside it. We can place an ultrasound emitter on one side. It will send out a wave. It will travel down, hit the edge of the box at the back, and travel back up to us. But also we can travel down and it can hit the crack and return back as well. So obviously we can determine if a crack is present because that echo time will be shorter, because it takes a shorter amount of time because it's traveling a shorter distance. Reflection. Reflection is the process in which you shine an incident ray over here, hits a smooth surface and is reflected back out again. This is the incident ray. The little angle over here from the normal out is called the angle of incidence. From the normal out to the reflected ray, this is called the angle of reflection over here. The law of reflection states that the angle of incidence is equal to the angle of reflection. I is equal to R. Then reflection and images. So right now over here, let's say you have an object and you're looking at it through a plane mirror. So here's a mirror. What happens is if you were to draw one ray of light from the top of the object hitting the mirror, going directly into your eye over here, and you draw another ray of light going from the top of the object into the mirror over here and going directly to the bottom of your eye, then you were to extrapolate these two lines, yes, extrapolate them, so obviously put dashes all the way back through the mirror, they would both meet at one point, and that is where the image is formed. This is a tricky concept. Make sure you try it with a piece of paper and a pen, because you need to get this right for the exam. Measuring the speed of waves in a ripple tank. So this is a required practical. This is how you're going to measure the speed of waves in a ripple tank. So you have a ripple tank over here and you have a vibrating bar. It's connected to a signal generator. So what happens is the metal bar is going to hit the ripple tank, and inside the ripple tank there is water, and what will happen is waves are going to be produced. Okay, you can control the frequency by the signal generator over here. Right, so look, as you can see, the metal bar hits it, waves are formed. But at the bottom, if you were to put a piece of paper, hopefully you can see that you will get a shadow of the waves over here. You get a shadow of the waves from above. Okay, right. If you need to put a meter rule down at the bottom as well, okay, and then the reason why is because you can work out the wavelength. So now, don't forget, this will be continuous, and it's really hard to see. The waves will keep forming each time. So you're going to take a picture of the bottom over here with the meter rule, and then you can work out the wavelength of the wave. So look, to work out the wavelength of the wave, you simply measure multiple of them and divide by the number of waves that there are. So there is 1, 2, 3, 4, 5, there's 6 over here. So 6 over here, there's total distance. I measure that value x, that distance, divide by 6, and that would tell me the wavelength. Now I've got the wavelength, I multiply it by the frequency, and then I'll be able to obtain the wave speed. The frequency is simply read off from the signal generator over here. Measuring the speed of waves on a string. So right now we have a piece of string over here is attached to a pulley and it's falling down. Here it is. Right, so you have a signal generator, oscillator, string, the pulley at the end of a table, and then the weights at the bottom. A length over here which you're going to measure using a meter rule. So you set it up as shown. You're going to try and work out the speed of these waves as well. So first of all, when the oscillator, as you change the frequency, you'll get different wave patterns being formed. Okay, so the wave patterns that you will see will be the following. So the first one you'll see is one complete loop, yes, for the first frequency, yes. Then as you crank up the frequency, you'll see 2 loops. And if you crank up the frequency even more, you'll see 3 loops each time over here. Right, so then we're going to get the following table. This will be the pattern observed, the frequency. So for the frequency you're going to get from the signal generator, you just write them down. They will all be multiples. So this one could be like 5 hertz, this one could be 10 hertz, this could be 15 hertz over here. The length is the length of the string from one end to the other. In order to calculate the wavelength, this bit is a bit tricky. You've got to spot how much the length represents a wavelength. So this bit from there to there, if I was you, just ignore the dash bit over here. That is half a wavelength. So just going up and down is half a wavelength. For the second one, we know that this length will be equal to a whole wavelength. So just look at that, that's one whole wave here. So the length is equal to exactly the wavelength. For this one, it's got 1.5. So this one, the length from one end all the way to the opposite end will be equal to 1.5 wavelengths. So therefore, to calculate the wavelength, I take the length which I measure, divide it by 1.5 for this one, and this one, the length will be equal to the wavelength, and this one, the length will be equal to half a wavelength over here. That's how you're going to get different values of the wavelength. And then to calculate the velocity, I take my frequency and then multiply it by the wavelength over here, and it will tell me the velocity. The electromagnetic spectrum is simply going to be a range of frequencies for electromagnetic radiation. They all travel at the speed of light, 3 times by 10 to the 8 meters per second. They can all travel through a vacuum. They can all be reflected, refracted, and diffracted. On one side, you've got radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, and gamma rays. As you go across the spectrum, the frequency increases and the wavelength decreases. The uses of them. So radio waves are used in radio and TV communication signals. Their microwaves are used for heating food and mobile phone communication. Infrared radiation is for thermal imaging and remote controls. Visible lights for photography, fiber optics. Ultraviolet is going to be detecting forgery and tanning beds. X-rays is going to be medical imaging. Gamma rays is going to be sterilizing equipment and treatment of cancer. The dangers: microwaves have a mild heating effect. Infrared can cause skin burns. Visible light can cause temporary blindness. Ultraviolet, premature aging of the skin/skin cancer. X-rays can cause cancer, and gamma rays can cause cancer as well. Note that ultraviolet, X-rays, and gamma are all forms of ionizing radiation. Ionizing radiation can cause mutations in the DNA within a cell, which can therefore cause cancer to be formed. X-rays. So first of all, just a little focus upon X-rays. X-rays are further down the spectrum over here. They're electromagnetic waves with a high frequency and short wavelength. They are a form of ionizing radiation. They can cause mutations and lead to cancer, but they can pass through certain materials and they are absorbed by certain materials. Hence why they are used in medical imaging. So now, how on earth are X-rays obtained? So this is going to be a 2D X-ray. So what happens is you place the subject on, like, let's say a piece of paper. This is going to be X-ray imaging paper. And what happens is you're going to bombard it with X-rays downwards. What will happen is that the X-rays can pass through certain materials, such as tissue. It can pass through it, but the bone it cannot pass through because the bone is a greater density. So as you can see, look over here. So the points of the sheet which are hit by the X-ray turn black. And as you can see, the X-rays can pass through the skin, hence why it turns black underneath where the skin is meant to be. But the bone over here blocks the X-rays over here, hence why the paper underneath is untouched. That's why it remains white. There we go. So the reason why the sheet of paper turns black is because it's been hit by an X-ray. If it looks white, it's because it has not been hit by the X-ray. It remains as before. And that's how an X-ray works. So X-rays can pass through certain materials only simply because of the density. The greater density, the less likelihood the X-ray can pass through it. But if the sheet gets hit by the X-ray, it turns black. CT scans. CT stands for computerized tomography scans, consists of objects being bombarded from X-rays in multiple directions. Multiple directions right now, not just from one way, from multiple directions you're going to get bombarded by X-rays, and it has it on a rotating camera over here. The data is then compiled together. The reason why is because now you can get a 3D image. Previously, it was a 2D image, yes, or top down, but now look, you can get a 3D image. Pros and cons. X-rays have a shorter burst of ionizing radiation. There's less exposure. It's a 2D image generated. There's less detail in the images. CT scans multiple bursts of ionizing radiation. There's a greater risk to the patient. A 3D image is created. The image can be rotated, but there's greater detail in the image. Visible light consists of the following colours: red, orange, yellow, green, blue, indigo and violet. Richard of York gave battle in vain. Yes, so on one side red has the longest wavelength, violet side has the shortest. So the frequency is increasing and the wavelength is decreasing as you go across. Then here is the colour spectrum. So there are three primary colours: red, green and blue, RGB. So there we go. Secondary colours, so red and green, the intersection will be yellow. Yes, red and blue, the intersection will be magenta. Green and blue, the intersection will be cyan over here, and all of them interacting with each other will produce white light over here. Now, why do some objects look a certain color? Right, so the rule is this: objects of color X will reflect color X and absorb all other colors. Right, so what that means is this: if I have a blue object, it can only reflect blue light. Yes, because the object is blue, it can reflect blue light. So if I shine white light onto a blue object, the blue light is reflected, hence why the object looks blue. If I shine white light onto a red object, red is reflected, hence why the object looks red. If I shine white light onto a green object, the green object can reflect the green light, hence why it looks green. But let's look at it within a bit more complex cases. So over here, if I have a cyan object and I shine cyan light into it, what happens is obviously the cyan can reflect the green and blue, hence why it can reflect the green and blue, and therefore the object looks cyan. If I have a blue object and I shine cyan light onto it, green and blue, what will happen is only the blue is reflected. Yes, so a blue object under cyan light will look blue. And let's say, for example, if I have a cyan going onto a red object, what color will the red object look? Well, don't forget the red object cannot reflect green or blue, so therefore it looks black. And if I have, there we go, another example, cyan over here, green and blue light being shone onto a magenta object. First of all, the magenta can only reflect blue and red, therefore it absorbs the green and only reflects the blue. So the magenta object will look blue under this light. Two more examples. Let's say I have a yellow object and I shine red light onto it. Don't forget, the yellow object can reflect the red and the green, so therefore it can reflect the red. Excellent stuff. Then if I have a cyan object and we shine red light onto it, The object cannot reflect the red, it can only reflect the green and blue, therefore this object looks black and nothing is reflected. Colors and filters now. So colors and filters. So a filter simply only lets certain colors through it. So let's say, for example, if I have white light onto a blue filter, the blue filter will only allow the blue to pass through. If I have white light onto the red filter, only the red one can pass through, and over here onto a green filter, only the green one can pass through. So hopefully that makes sense. And look at the bottom example. If I have blue light onto the red filter, what will happen is that the red filter will absorb the blue and nothing will pass through. Then we've got a couple examples over here. Let's say I've got white light onto a sine filter. Obviously the green and blue pass through and the red is not. If I've got white light onto a yellow filter, obviously the red and green can pass through but not the blue. And look, if I've got two filters, one in front of the other, and I shine white light into it, so red, the green and blue, which is in white light, go into the magenta filter, the red and green can pass through. But if I place another red filter in front of it, only the red one can pass through. Seismic waves is another word for earthquake waves. Right, so you've got to be able to be aware of the structure of the earth. On the outside we've got a solid crust, then we've got a solid mantle, then we've got an outer core made out of liquid, then an inner core made out of solid. Then from here we've got if an earthquake occurs over there, the epicenter is the point directly above the earthquake's origin where it hits the surface. So the earthquake's origin is over here, and this is the point of the surface right above it. So this is the earthquake origin, this is the epicenter. Seismic waves, there are two types of waves. There are P waves and S waves. The P waves arrive first and then the S waves arrive afterwards. The P waves are longitudinal, the S waves are transverse. P waves are faster, that's why they arrive first. Yes, S waves are slower, that's why they arrive second. The P waves can travel through solids and liquids, the S waves can only travel through solids only. And look, I've got this diagram over here. Let's say the earthquake occurs there. P waves will travel upwards, hit the Earth's surface, and S waves will also travel upwards and hit the Earth's surface over here. But let's say we have an earthquake on one side of the Earth over here. First of all, we can see that the P waves can travel through everything. Yes, the reason why P waves can travel through solids and liquids. But S waves cannot do the same thing. They are not doing the same thing over here. We can see that if an earthquake occurs, the S waves take a different path. They cannot pass through the outer liquid core. So that's why there is a shadow zone over here where no S waves are detected. Distance calculations. So let's say, for example, an earthquake occurs over here and it travels and hits the surface. First of all, we know that the distance the P wave travels will be the same as the distance the S wave travels over here. So therefore, we can write dP is equal to ds. And let's say there's a time interval. Let's say the S wave arrives x seconds after the P wave. Therefore, we can say that the TS, the time taken for the S wave to arrive, is equal to TP plus x. So therefore, I can plug it into our formula. So we can see that velocity of the P wave times by the time of the P wave is equal to the velocity of the S wave times by the time of the P wave plus x. Don't forget, this is the time of the S wave, which we said up above over here. Make sure you can see that relationship and you can manipulate it and rearrange it if required. Location of earthquakes and triangulation. So let's say we have 3 seismometers which are going to detect the earthquakes. First of all, the seismometer can only tell you how far away it is, so it could be anywhere along this line. But if you put 3 of them up to find the location of the earthquake, it will be where all of the lines intersect. So this point over here, that will tell me the exact location of the earthquake. Refraction. Refraction is going to be the process in which a wave changes direction as it enters a new medium due to a change in speed. So right now we've got, let's say, a boundary between air and glass. The wave is traveling, hitting it, then going to refract. Yes, it's going to refract over here. We can see that as you go from less dense to more dense, you bend towards normal. And as you can see that if we're going for the reverse, if we're going from more dense to less dense, you bend away from the normal. So if you're going from less dense to more, your speed decreases, yes, and you bend towards normal. And as you go from more dense to less, your speed will increase, yes, and you bend away from the normal. Investigating reflection and refraction. So this is a required practical. You need a perspex block, a ray box, plain paper, ruler, and protractor. You're required to look at how refraction takes place and reflection. So you place the block onto a piece of paper, you draw around it, there we go, and then you mark where the ray of light is going to enter via the ray box, and you mark where it's going to exit from the glass block. Then once you're done with that, you remove the glass block, you connect the line over here, and then you can measure the angle of incidence, the angle of refraction, yes, which is this angle, and the angle of reflection. So don't forget, you're taking the angle of incidence, angle of reflection, and angle of refraction. This is quite a tricky practical. Make sure that you state that you have to remove the block and then connect the line. The risk assessment, do not look directly into the ray box. It can cause temporary blindness. Control variables, you must keep the perspex block the same throughout the experiment. Sources of error, difficulty in identifying the midpoint of the ray of light when marking, because it's quite difficult when you're using the ray box, and when there's very small angles, it might be difficult for you to take those measurements. Here's some sample results. Let's say, for example, this is going to be angle of incidence, angle of reflection. These two angles should be the same, yes, because they should obey the law of reflection. But for the next one, for the angle of incidence and the angle of refraction, this one over here, we can see that as the angle of incidence increases, you keep increasing the angle of incidence each time. Don't forget, you're going to increase each time and record the different values. The angle of refraction will be increasing, but will always be a bit lower. So as you can see, it's going 0, it's lower over here. So the first set of data will give me this graph, and the second set of data will give me this graph over here. Lenses, there are two types of lenses, converging lenses and diverging lenses. Converging lenses are also called convex lenses, and diverging lenses are also called concave. These are my symbols which you will see. Yes, the arrows pointing outwards will be converging, diverging, the arrows will be pointing inwards. Right, so first of all, when parallel rays of light travel and they go through a lens, they will be focused towards the focal point. If it's a converging lens, don't forget the word converge means to drag them towards. So all these rays of light, they go through it and they converge towards a point over here, then they will separate out again. The focal point is the point where they all meet. The focal length is the distance between the lens and the focal point over here. Next one, if we have parallel rays of light hitting a diverging lens, the parallel rays of light hit it and they're going to spread out over here. Then you might be asking me, how do I know which angle they're going to move off at? It's because if you were to extrapolate the lines backwards, they will all meet at this point over here. This will be called the focal point, where they all meet over here. Right, and this will be for a diverging lens. The lenses and the eye. So right, this is the eye and it's a lens. First of all, parallel rays of light should enter the lens and should travel down and hit the back of your retina over here. This will be 20/20 vision. But if somebody is short-sighted, the rays of light will just focus too early. So the solution will be the following. You want to spread the rays of light. That will be a diverging. To diverge, it's going to spread it. Hence why you put a diverging lens in front of somebody who is short-sighted. The reverse, let's say if somebody is long-sighted, the rays of light will converge behind the retina. So you want to converge it earlier, so you place a converging lens in front of it. And hence you can see that the rays of light have been converged to the back of the retina over here. Let's say we were to draw ray diagrams right now for lenses. So first of all, this looks a bit complicated at the start. You have the lens in the middle, you have a principal axis over here. You've got the focal point, F, which is symmetrical on both sides, and 2F, which is double the focal point on each side as well. So the object is the red one. So first of all, to draw this, you draw one ray of light from the top of the object directly for the center of the lens. Yes, going through it. Then one ray of light going directly horizontally across along this axis, hitting the lens and then going through the focal point. Where these two rays meet, this is where the image is formed. The image will be diminished, inverted, and real. Then if we move the object in between F and 2F, we can see that the image changes. So right now, if I move the object between F and 2F and do the same thing again, one ray of light from the top of the object through the center of the lens over there, one ray of light horizontally across and then through F over there, we can see that the image is formed much larger than before. So previously it was like this. Yes, it's smaller. Then look, the position of the object changes the nature of the image at the end. So yes, you can see right now that the image is magnified, it's inverted, it's upside down, and it's real. The magnification is equal to the image height divided by the object height. So if you want to calculate that, you simply measure the image height divided by the object height. That will tell you the magnification. Next, if I was to move the object in between the focal point and the lens over here and do the same thing again, one ray of light from the top of the object through the center of the lens, one ray of light horizontally across through the focal point over here, hopefully you can see these two rays of light will not meet. I can extrapolate them both backwards and they will meet at this point at the top over here. So now look, the image is formed on the same side of the lens. Right now it is magnified, it's upright, and it's virtual. It is a virtual image because it is not producing real rays of light, and we have extrapolated these lines backwards, both of these two over here. Next of all, diverging lens. So the diverging lens is a little bit tricky. But first of all, if we have the object over here, you still draw one ray of light going from the top of the object through the center of the lens, one ray of light going horizontally across, then it's going to move away. Don't forget which angle is it going to move away at. It must line up with the focal point. So that angle, this line, must line up with that focal point over here. And then I extrapolate this line backwards, and where the extrapolated line meets the other line over here, this is where the image is formed. So first of all, we have a bar magnet over here. A region around a bar magnet in which a magnetic material can experience a force is called a magnetic field. Over here we can see that the field lines go out of the north, yes, out of the North Pole and into the south. And that's why I have the arrows over here. We know that there are three magnetic materials, iron, nickel and cobalt. And like poles will repel and opposite poles will attract. That means you put two north poles, they will repel, or two south poles, they will repel. But if you put a north and south, they will obviously attract over here. Compasses and magnetic fields. If you were to be given a bar magnet, you can determine the direction of the magnetic field by simply taking a plotting compass, the ones with a needle inside which turn, and placing it at different points around the bar magnet. As you can see, when we place the compass at different points, the compass needle will follow the field lines. So as you can see over here, it follows this line over there, and this needle over here follows this line over here. So therefore you know that this one will be the south pole because the lines go in, and this side will be the north pole because the arrow is going away. So that's why they also call compasses south-seeking, because they're always pointing towards the south pole. Compasses and the Earth's magnetic field. If someone was to give you a navigational compass and you were to take it out, hopefully you recognize that it would always point to the North Pole. The reason why is because that we know that the magnetic field lines of the Earth will match up with the compass needle. So look, inside the Earth there is a bar magnet. You can visualize it as a bar magnet. And look, the field lines go out of the North Pole and therefore into the South. Yes. I know that's a bit confusing at the start because you're like, hang on a minute, isn't the North Pole at the top? Yes, the geographic North Pole is in fact the magnetic South, and the geographic South Pole is in fact the magnetic North. And we can verify this by using a navigational compass, because we know that when we take out a navigational compass, it will line up with the magnetic field, which is pointing upwards over here. Induced magnetism. So what happens when you are to bring an iron block next to a bar magnet? What will happen is the iron block will be attracted to the bar magnet. How does this happen? Well, first of all, it temporarily creates its own magnetic field within itself. So look over here, what happens is it makes the opposite pole. So if you have a south pole of a magnet facing it, it makes a north pole and the opposite end becomes south. And therefore it is attracted and therefore it moves across. This is only going to last for a temporary amount of time, and therefore this is not permanent. So therefore if you move the iron block away from it, eventually it will lose its magnetism. This whole process is called induced magnetism. Electromagnetism. So over here we have a circuit and we have a switch, and look, we have a wire going round, and look, it coils round over here. So the wire coils round, going up around the back, down around the front, coiling round over here. This is called a solenoid, a coiled wire. So we have a piece of iron next to it. Right now, nothing's happening. The iron block is not attracted. But what happens when we press the switch? When we press the switch, hopefully we recognize that current will flow through the wire. Yes, current flows through the wire. Don't forget, the current will go out of the long positive terminal over here and all the way around over here. Now current passes through the wire. What will happen is a magnetic field will be induced within the solenoid. So look, we have a magnetic field induced within the solenoid. And obviously, if we have a magnetic field induced within the solenoid, it can now attract the iron block. So the piece of iron will move towards it over here. There we go. And obviously, this is a temporary magnetic field, because if I were to turn off the current, it will stop having a magnetic field. There are three ways to increase the strength of the magnetic field. Number one, by increasing the number of coils per unit length. So if I wrap them closer together. Number two, by increasing the current. And number three, by inserting an iron core through the coils, is the third way to increase the strength of the magnetic field. Electromagnets and the school bell. So this is the use of electromagnets. Over here we have a circuit, power supply over here. Then as you can see we have the solenoid over there. And this point is just like, let's say this is a metal arm, just a piece of metal, and there's a hinge point at the top. So there's a hinge point. The hinge point means that basically the metal arm can move, swing about that hinge point over here. So, and here's a gong and this at the bottom. What happens if we were to press the switch? Hopefully you recognize that when we press the switch, current will flow through the solenoid. Okay, current flows through the solenoid. We know that it's going to generate its own magnetic field, which is why it's in yellow. The magnetic field generated will therefore attract the iron bar. So it will then swing outwards and hit the gong, making the noise. Right, so as it hits the gong and it makes the noise, what will happen is the circuit will become broken. Okay, so if the circuit has become broken, what will happen is the magnetic field will therefore shut down. and therefore the metal arm will fall back into place once again, and then the whole process will start again. That's the reason why it gets hit repeatedly, again and again, due to electromagnets. The right-hand rule, so linking electricity and magnetism. So if you were to take your right hand, yes, your right hand, you were to hold it up, give yourself a thumbs up. So right now what's going to happen is your thumb is going to represent the direction of the current, and your fingers are going to represent the direction of the magnetic field. So the current goes up, the field is going this way. And obviously if I was to reverse the direction of the current, the field is going to swap direction. That's going to be important later on. Representing current into and out of the page. A circle and a dot simply means that the current is coming out of the board. Yes, the best way to visualize it is going to be, imagine if I was to throw a dart at you. First of all, if the dart is traveling towards you, you'd see a dot. That means that it's coming towards you. If the dart was moving away from you, you'd see the fins which are crossed. Hence why we're going to use the symbol of circle and a cross to mean into the board or moving away from you. So circle and dot means out, and then circle and cross means into the board. So if you were asked the following, so if somebody was to draw the current going into the page, so circle and cross, which way is the magnetic field? Well, take your thumb, point it into the page right now, or into the screen, and therefore you can see it's going to go clockwise in that direction. And if you were to have the current pointing towards you out of the screen or out of the page, first of all, take your thumb, point it towards you, and we can see the current is going to go anti-clockwise over here. So this is how we can determine the direction of the field based upon the current. Force on a conducting wire within a magnetic field. So over here we're going to have a circuit. Yes, so look, we've got a cell over there, switch, and a wire. Yes, connected all the way around over here. We're going to then place that within a horseshoe magnet. Basically, it's a north and south pole normal bar magnet. We're just bent into a horseshoe shape. First of all, recognize that the magnetic field lines are going to go out of the north into the south. Yes, so the magnetic field lines are going to go from the north pole to the south pole. If you were to then press the switch, what will happen is current will flow through the wire. When current flows through the wire, we know that every single wire which has current flowing through it will generate its own magnetic field. So the magnetic field is therefore induced around the wire. So now there's going to be a magnetic field from the permanent magnet, from the horseshoe magnet, and there's going to be a magnetic field from the wire. Both of them will interact, and therefore the wire will experience a force. So both of them will interact and the wire will experience a force. We can use Fleming's left-hand rule to determine the direction in which that wire will move, which we'll do in a moment. Fleming's left-hand rule. Fleming's left-hand rule can be used to determine the direction of the force on that conducting wire. So first of all, take out your left hand now. So best way to do it is going to be FBI. F stands for direction of the force. B stands for direction of the magnetic field. Over there I'll put down magnetic flux density, but still the direction of the field, and I is going to be the current. Notice they're all 90 degrees towards each other. You must have the wire perpendicular to the field, and therefore you will get a force. So in this diagram over here, you can clearly see that the field is going across, yes, and therefore we know the current's going into the page. Make sure you can see that, it's going into the page, therefore the force is down. And then at the bottom I've got 1, 2, 3, 4 more examples in which I've drawn the sideways on view. So obviously over here we can see the current's going in, so look, verify it, we can see the force is down. Pause the video and make sure you can try these examples yourself. More practice on Fleming's left-hand rule. So over here I've got 1, 2, 3, 4 diagrams, and they're slightly different. Look carefully, they're slightly different. What you're going to do is you should be able to take out your left hand and verify the direction of the force. Don't forget, when you're using Fleming's left-hand rule, you should do the field direction first, then rotate your hand for the current. So do the field first, rotate your hand for the current, and then you can determine the direction of the force by which way your thumb is pointing. Force on a conducting wire within a magnetic field, and F is equal to B. Right, if you actually want to calculate the value of the force, first of all we can use the following formula. F is equal to BIL, where F is the force, B is the magnetic flux density, I is the current, and L is the length of the wire within the field. The force is measured in newtons, magnetic flux density is measured in Tesla, the current is in amps, the length of the wire is going to be in meters. It's only going to be this length within the field over here. The DC motor, right, so this is going to be the physics behind how we have a motor spinning. So there is a coil of wire over here, and it's a square coil right now. It's a square coil of wire. We're going to place it in between a north and south pole. Right, so that's my wire, A, B, C, and D. And we're going to pass current through the wire over here, through A. We can see it's going to go to the left, up, then from B to C, down, and then back again over here. So now there's a current flowing through the wire. Right, we know there's current flowing through a wire, and parts of the wire which are perpendicular to the field will experience a force. So I've drawn this a bird's eye view of this over here. Look, so this is a north, and that's that wire, just a bird's eye view. We can hopefully see that A to B, the current is perpendicular to the field, and C to D, the current is also perpendicular to the field, but they are both in opposite directions. So A to B, there will be a force downwards, verify it using Fleming's left-hand rule. C to D, there's a force pushing it upwards. And therefore, if AB is moving down and CD is moving up, the whole thing will rotate. So the whole thing will rotate here, and that's going to be the origin of the physics behind a DC motor. Right, so the DC motor, this is the full diagram right now. So first of all, there is a split ring commutator over here. So imagine a ring which has now been split. That's going to be the split ring commutator. And then there's a carbon brush over here. So current's going to pass in from this side and look, going to enter via the carbon brush. The reason why we put a carbon brush is therefore that there's going to be a connection, but it can rotate freely. So as this rotates round, there will always be a connection because the brush can just swap round to the next terminal. As the coil rotates, we notice that the split ring commutator on the right is going to obviously get to the position on the left-hand side over here and will rotate round. This ensures that the current always enters from the same side and therefore ensures a full complete rotation. The generator effect is the process of generating voltage from the movement of magnets into coils. Yes, you either move the magnet into a coil or the coil into a magnet, and this is known as the generator effect. When a wire or coil experiences a changing magnetic field, a voltage is induced. So when a wire or a coil experiences a changing magnetic field, a voltage is induced. And I've got two diagrams right now. So the first diagram, we've got a voltmeter and we've got a solenoid over here, just a coil of wire. We notice that when we push a bar magnet into it, we'll get a voltage one way. Yes, so a voltage is induced. The reason why is because the coil is experiencing a changing magnetic field. Because initially there wasn't a magnetic field going through it. Then as you put the bar magnet in it, we notice that the coil experiences a changing magnetic field. As you move the bar magnet out, notice that the voltage will actually swap directions. So if you move the bar magnet in, the voltage goes one way. If you move the bar magnet out, the voltage goes the opposite way over here. So the voltage can be induced by moving the bar magnet into the coil. In order to get a greater magnitude of the voltage, to get a greater value of the voltage, you can simply move the magnet faster, or you can use stronger magnets, or by increasing the number of coils per unit meter. So by increasing the number of coils, you would therefore generate more of a voltage if you move that bar magnet in. Second method to generate voltage is the following. So over here, rather than moving the bar magnet into the coil, we're going to move a wire within a magnetic field. So look, we've got our horseshoe magnet over here, and look, we've got a voltmeter and a wire in this diagram. There is no power supply. You're going to take the wire and you're going to move it up and down within the magnetic field. When the wire moves within the magnetic field, we notice that it will cut the magnetic field lines, and therefore it will generate a voltage. So moving the wire upwards, we'll get a voltage one direction. Moving the wire downwards, we'll generate a voltage in the opposite direction over here. There are three ways to increase the size of the voltage induced. Number one, it's going to be by moving the wire faster. Number two is by using stronger magnets. And number three, by putting more wires within the field. So if you put more wires within the field and you move them all, you will generate a greater amount of voltage at the end. So don't forget, you need to be experiencing a changing magnetic field to induce a voltage. Generators. So over here we have a DC generator, also called a dynamo. So a DC generator, the DC stands for direct current. Look at this diagram, it looks almost similar to the DC motor, but instead of a power supply, there is a voltmeter. We still have the split ring commutators and we still have the carbon brushes. So the difference between this one and the DC motor is that in a DC motor, you're passing current through and it's getting forces and they're turning. Now, in this diagram, you are going to turn it. You are going to turn that square coil within the field. So you must turn the coil within the field and a voltage will be induced. And don't forget, because we've got the split ring commutators, it only produces DC voltage. So therefore, every half turn, so when this rotates halfway, we get to this point. Rotating it one full rotation, we do it and we get to this point over here. AC generators. AC generators are not the same as the dynamos. The reason why is because they do not have the split ring commutator. They have a slip ring over here. So look, we've got two rings over there, complete rings this time. One part of the wire is connected to this ring. The other part of the wire is connected to this ring over here. They never swap over. They never swap over. So what happens is now when the coil rotates, is simply, rather than getting a DC voltage out, we then get an AC voltage being produced. We get an AC voltage because there is no longer the swapping of terminals with the carbon brushes, which we had previously with the DC generator. So this one, the split ring, the generator, which is AC, will only have a slip ring over here. Loudspeakers. How do loudspeakers work? Right, so this is quite tricky the first time you look at it. So first of all, there is a bar magnet over here, and north and south over here going around, and we have a speaker cone in between. There are coils wrapped around the speaker cone. So what we're going to do is this. You're going to pass current through the coil. Right, so when you pass current through the coil, what will happen is it will generate its own magnetic field. But there is already a magnetic field from the permanent magnet. The magnetic field around the coil over here will interact with the magnetic field from the permanent magnet. The two fields interact, therefore it causes a force to be experienced by the cone, and the cone will move outwards. Okay, then how would the cone move inwards? Don't forget it's a loudspeaker, it should pulse. So in order to move the cone back inwards, all you've got to do is simply reverse the direction of the current, and therefore it will experience a force in the opposite direction, and therefore it moves back in. That's the reason why you have the AC supply for a loudspeaker. Microphones. Microphones are a bit different. So microphones, you're going to speak into the microphone and it's going to generate a voltage. So look over here, we've got a microphone receiver and we've got it within a magnetic field once again. So when the sound waves come in, it pushes the microphone receiver into the magnetic field. So it pushes all these coils into that magnetic field. These coils therefore experience a change in magnetic field, and therefore a voltage is induced. So the coils of wire enter the magnetic field, and therefore because they are experiencing a changing magnetic field, a voltage is induced. So this one is the generator effect over here, because you're going to be generating voltage. So obviously as the sound wave goes in, it generates a voltage, and as you move the coil out again slightly, it generates a voltage in the opposite way. So as the sound wave comes in, the movement of the coil is going to obviously match the frequency of that sound wave. Therefore, it converts the sound waves into an electrical signal. Make sure you understand the difference between the loudspeaker, which is basically the motor effect, because you'll need it to make motion, and the generator effect is going to be in the microphone because you're going to be generating the voltage, because that wire is experiencing a changing magnetic field. Transformers. So, basics of transformers. First of all, if you want to transmit electricity from a power station to your home, surely you need a very large cable, yes? But if you were to use a high current to do this, what happens is when high current passes through a wire, it heats up, and when the wire heats up, energy is wasted. This is very inefficient. Therefore, we use transformers. Transformers, there are two types. Number one, there's a step-up transformer and there's a step-down transformer. Don't forget, we're going to go from the power station to your home. So first of all, high current comes out of the power station at a low voltage. The step-up transformer is going to step up the voltage to reduce the current. So it steps up the voltage to reduce the current. And therefore, the electricity is transmitted at low current but high voltage. Then when it gets to the step-down transformer, what's going to happen is it's going to step down the voltage to increase the current. So it steps down the voltage to increase the current. How does this work? Well, you can use the power equation to visualize it, because as you increase the voltage for the step-up transformer, the current decreases for the power to remain constant. And for the step-down transformer, as you are decreasing the voltage, yes, therefore the current is increased again to keep the power constant. Transformers and how they work using magnetism. So this is going to be the structure of a transformer. It is a giant iron block over here, and it's got coils of wire around the first terminal over here, and it's got coils of wire wrapped around the second terminal over here. It's made out of iron, everyone. This one is called the primary coil, this is called the secondary coil. The wires themselves are insulated. The wires are insulated, and there's a alternating voltage which is going into the primary coil and a voltmeter at the end on the secondary coil over here. Step-up transformer. To identify a step-up transformer, we know that there are going to be more coils on the secondary coil than the primary. For a step-down transformer, we know that's going to be more coils on the primary than the secondary. So look, we're going to have NP represents the number of turns on the primary coil, NS represents the number of turns on the secondary coil. How do transformers work? So first of all, you pass current through the primary coil. Hopefully you recognize that when current passes through the primary coil, a magnetic field is induced. Now the magnetic field is induced, don't forget this is made out of iron. Therefore the magnetic field can flow through the iron core right now. Excellent stuff. As the secondary coil is now experiencing a changing magnetic field, a voltage will be induced. So look over here, we can see that as the secondary coil experiences a changing magnetic field, a voltage will be induced due to the generator effect. And that's why we have the voltmeter at the end over here. In order to ensure that the magnetic field is constantly changing, I simply have to reverse the current in the primary coil. Because when I reverse the current in the primary coil, it swaps the direction of the magnetic field. You need to have a changing magnetic field in order to have a voltage being induced constantly. Transformer equations. There is an equation to link the number of turns in the primary, number of turns in secondary, and the voltage in the primary and the voltage in the secondary. It will be the following. NP over NS is equal to VP over VS, where VP is the voltage in the primary coil, VS is the voltage in the secondary coil, NP is the number of turns in the primary coil, and NS is the number of turns on the secondary coil. There is another formula relating the current and voltage in both the primary and secondary coils. First of all, the power entering it must be the same as the power out. We also know that power is equal to current times by voltage. Therefore, the current in the primary times by the voltage in the primary will be equal to the current in the secondary times by the voltage in the secondary. So, the Sun is our nearest star. All the planets in the solar system orbit around it. We've got the Sun over here, we've got Mercury, Venus, Earth and Mars, Jupiter, Saturn, Uranus, Neptune. There used to be a planet called Pluto, but it got demoted. So I memorized the following. My very easy method just sums up 9 planets, but obviously Pluto is no longer a planet, so you can just remove that. We have the inner planets over here and the outer planets over here, and they are separated by the asteroid belt. Orbit. When an object goes around another object in a circle, we know this is going to be experiencing circular motion. So this whole thing is called circular motion because it's moving around in a circle. Right, the force pulling you to the center of the circle is called the centripetal force. For the Earth going around the Sun, we know that centripetal force is going to be provided by gravity. Gravity is going to be pulling it inwards. We can see that as the object moves around, that its velocity is changing because it's changing direction over here. So we can say that it's being pulled in one direction and being pulled in one direction over here, so that's the reason why it moves in a circle. Although the Earth is moving at a constant speed, it will be accelerating. The reason why is because acceleration is going to be a change in velocity divided by the time taken. And although it's moving at a constant speed, the reason why the velocity is changing is because the direction is constantly changing. So as you have a change in velocity divided by time taken, therefore it will be accelerating. So therefore objects moving in circular motion will be accelerating inwards. Orbital velocity. If you want to work out the orbital velocity of an object, basically it's going to be the distance travelled in one rotation divided by the time taken. So if we have the Earth going around the Sun, the distance travelled in one rotation is going to be the circumference of the circle, which is going to be 2 pi r. The time taken for it to go around is going to be the time period capital T over here. That's why to calculate the orbital velocity it will be 2 pi r divided by t, where r is the distance between the Sun and the Earth. Satellites. There are 2 types of satellites, naturally occurring satellites and artificial satellites. Natural satellites are going to be the planets, the moon, because the moon is a natural satellite of the Earth. The planet is a natural satellite of the Sun. Artificial satellites are man-made and they've been placed up there by the human race. Geostationary. Geostationary, look, the key is in the wording. Geo means the Earth, stationary means not moving. Geostationary satellites stay above the Earth in the same position. It has the time period as the time period of the Earth's rotation, so it rotates with the Earth. So let's say this is the Earth over here, my calculator. The satellite will be my hand over here. So as the Earth rotates, the satellite stays in the same position above the Earth. There we go. So it rotates in the same position. Its use will be in communication satellites because let's say for mobile phones, you always want to have reception. So you always want the satellite directly above you in the same position. Polar orbits. Polar orbits are different. Polar orbits, as the Earth turns around, yes, first of all, it doesn't move with it. It actually sweeps from pole to pole. So let's say the Earth is rotating around. We can see the satellite is going to sweep from pole to pole. The reason why you want this is because it can be used to cover the entire world. It's useful in weather mapping and for spying on other countries because therefore you can actually look at what every other country is doing. The life cycle of a star. So this is the life cycle of the stars that were first created in the universe. Initially there is hydrogen, dust and gas. Right, then gravity acts upon it and brings it together. It starts to clump together. Eventually it takes the shape of a protostar, which is spherical in shape, and the temperature starts to increase. No light is given off yet, and there's not enough temperature for nuclear fusion to occur. Then it becomes a main sequence star when the temperature is hot enough. And now we have the nuclear fusion occurring. Hydrogen is being fused into helium. So hydrogen fused with other hydrogen to make helium, and energy is released in that process in the form of heat and light. Then from here, the star will spend most of its life in this stage. The reason why is because it has a nice balance of the gravitational force pulling inwards and the force from the radiation pressure pushing outwards. Both those forces are going to be equal, hence why it has this most stable phase. Then from here, from the main sequence phase, it can take two paths. The one on the left hand side is for a star the same size as our sun. It will expand out to become a red giant. Then as the hydrogen runs out, the fusion of helium occurs with lighter elements up to iron. So iron is formed over here. Then eventually the outer layer sheds off, leaving a hot white dwarf. Eventually this will cool down to become a black dwarf. So that's for our sun. Our sun will take this path, yes, over here. But if it is much larger than the sun, it will go down another path. For the larger stars, it will expand to become a red supergiant. As it becomes a red supergiant, yes, what will happen is the hydrogen will run out again, and yes, we'll get the fusion of the heavier elements up to iron. Yes, the helium fusion occurs here. Then it will contract very rapidly, and what will happen is a violent explosion will be observed called a supernova. This is where the elements greater than iron are being fused. So when you find uranium, the uranium is not formed anywhere else except from the supernova. Now it is formed in a supernova, it is then scattered across the universe. And then from here it can even become a neutron star over here, which is a density packed star, or it can become a black hole, which has a very strong gravitational pull that even light cannot escape it. The formation of our solar system and planets. So how is our sun formed? Our sun is not the same as some of the stars which were previously created, because we actually have hydrogen at the start, but we also have heavier elements from supernova explosions from earlier stars. So earlier stars obviously made these heavier elements, and now our sun is going to be formed from the remnants of dead stars. So look over here, now we have all the elements clumping together once again to form a protostar over here. And look, we can see that not all of it clumps together. But what's going to happen to all the material that's not clumped together? Hopefully you can recognize that those bits which have not clumped together will then clump together themselves. So the dust clouds which were not used in the formation of the star now clump together due to gravity, and these will form the planets, and that's how we have the planets. Note that there are heavier elements still in these, so you get the heavier elements in these planets being formed. The inner planets of the solar system have solid surfaces because they are made up of heavier, denser materials like iron or uranium. Gravity is stronger, closer to the sun, hence why these heavier materials can be easily brought together. The outer planets are called gas giants. This is because the gas substances contracted together further away from the sun. That's the reason why we have the gas giants further away. The Doppler effect. So let's say, for example, we have an ambulance over here. We have a person behind it and a person in front. Initially, if the siren is turned on, you would hear the same thing from both sides. Same thing from both sides because the waves are coming out equally. But what happens when the ambulance starts to move to one side? So when the ambulance starts to move to this side over here, what will happen is these waves get bunched up. So the person on the right will have a higher frequency. So the person on the right will observe a higher frequency and a shorter wavelength. It is a shorter wavelength because the distance between each one is shorter. The person behind, watching it leave, is going to experience a lower frequency because the wavelength has been stretched out. This is known as the Doppler effect. The apparent change in the frequency and wavelength of a wave due to the relative motion of the source, in this case it's the ambulance, and the observer is known as the Doppler effect. So make sure that you understand it's due to the relative motion of the source and the observer. So it depends on where you are. Yes, if it's moving towards you, high frequency, if moving away from you, it's going to be a low frequency. Now we are going to use our understanding of the Doppler effect when we're talking about light. Right, so first of all, this is the visible light spectrum. Red, orange, yellow, green, blue, indigo and violet. Yes, Richard of York gave battle in vain. One side we're going to call the left hand side the red side, and the right hand side is going to be called the blue side for now. So we've got the left hand side and the right side is going to be called the blue side. Right, now from here we're going to say that white light has an equal distribution of all the wavelengths, so we're going to put it right bang in the middle. It'll be like the average. So imagine that red line over here. I'm going to use this red line to explain the concept in a minute. So just for now, just accept that the red line represents white light. Now, let's talk about galaxies. So let's say a galaxy is going to emit white light. Yes, over here. Right, if the galaxy is stationary, yes, it emits white light. But then if the galaxy is moving away, we notice from the Doppler effect that the wavelength will increase. Yes, the waves get stretched out. The wavelength increases and the frequency drops down. Now, because the white light has increased in wavelength, what will happen to the white light over here? Well, obviously if you've increased in wavelength, you have shifted to the red end of the spectrum. Hence why we call it redshift. So the white light increases in wavelength, therefore shifting it to the red end of the spectrum. That's why it's called redshift. So if a galaxy is moving away from us, we can see that the wavelength has increased. The white light is shifted to the red end of the visible light spectrum. This is therefore called redshift. And the opposite then. So what happens if we observe a galaxy and the galaxy is moving towards us? Hopefully you can see that the wavelength has decreased. If the wavelength has decreased, the white light will shift to the blue side of the spectrum because the wavelength has decreased. So the white light shifts to the blue side of the spectrum. So therefore we can say that the white light is shifted to the blue end of the visible light spectrum. We call this blue shift. So make sure you understand the idea of red shift and blue shift in terms of the Doppler effect and how the wavelength is changing due to the motion of the galaxy relative to the observer. So how do we actually see red shift and blue shift? Well, we can see them via absorption lines. Basically, this is a spectrum. On one side it's red, one side it's blue. Yes, it's going across the entire color spectrum. And we have these black lines over here. The black lines are basically like a fingerprint for that galaxy. Right, so the one in the middle is not moving. That's the reason why they have lines like this. But the one above is an absorption spectrum from a galaxy moving away from us. The key thing to note is that, as you can see, that if the stationary galaxy has lines like this, and the one moving away from us, what's happened to all those lines? Look, they've been all shifted. This one, this one, this one, this one, this one, and this one. They've all been shifted to the red end of the spectrum, hence why we know this is going to be redshift. And look, the one at the bottom over here, relative to this one over here, we can see that all the lines have been shifted to the blue end of the spectrum, hence why this one is going to demonstrate blue shift. So by looking at the absorption lines, we can determine if it's going to be redshift or blue shift. Redshift and expanding universe. Right, so if we were to plot a graph of the velocity of the galaxy in kilometers per second on the y-axis and the distance of the galaxy from Earth on the x-axis, we will know that the galaxies furthest away are moving off the fastest. And therefore they will exhibit the greatest redshift. Sometimes when you're looking at these questions, they might have the unit of the light year. The unit of the light year is not a measure of time, it is a measure of distance. It is a measure of the distance traveled by light in one complete year. In order to calculate the value of 1 light year, I'm going to take the speed of light and times it by the number of seconds in a year. So the speed of light is 3 times by 10 to the 8 meters per second. Therefore, I'm going to times it by 60 times by 24 times by 365, which is going to be the total number of seconds in a year. Then my answer will be 9.4 times by 10 to the power 15 meters. So yes, 1 light year is equal to 9.4 times by 10 to the power 15 meters. Pause the video and check my calculation to make sure that you understand how we calculate that. A little bit of extra information over here, that we know that the velocity is proportional to the distance, and therefore that there's a constant which relates to both of them. That constant is going to be called Hubble's constant. The gradient of the line is going to be 1 divided by time. So therefore, to work out the time of the universe, if you rearrange this formula, t is equal to 1 divided by the gradient of that line, where t will be the time of the universe. So if they give you this graph and you're asked about the time of the universe, it is basically 1 over the gradient of this line. So what does redshift tell you about the universe? Well, from Earth, every galaxy which is observed, you will be able to observe redshift. So redshift is observed from every single galaxy. So obviously if redshift is observed, that tells you that all the galaxies are moving away and therefore the universe is expanding. The Big Bang Theory. The Big Bang Theory is the most accepted theory based upon the evidence on how the universe began. The Big Bang Theory states that from one point of singularity, a giant explosion of energy occurred and the universe was created and has been expanding ever since. There are 2 types of evidence supporting the Big Bang. The first one, which we just covered, is going to be redshift. You observe redshift from distant galaxies. This shows you that the universe is expanding. The other bit of data to help support the Big Bang Theory is going to be the detection of CMBR, which is going to be cosmic microwave background radiation. It's basically the leftover radiation from the initial Big Bang, so the leftover radiation. The fate of the universe. Right, so we don't understand how the universe is going to end, but currently if we plot a graph of the size of the universe versus time, we're roughly over here. We recognize that it can go down the possible route of the big yawn, it continues to increase in size, or it goes down to the big crunch. Maybe it will collapse back inwards on itself over here, we're not too sure. Unknown aspects of the universe. So the universe is actually expanding at an accelerating rate. Because it is expanding at an accelerating rate, physicists are not too sure what is responsible for this expansion. They have called it dark energy because they are not too sure what it is that's causing the acceleration in the expansion of the universe. Dark matter. So here we have a spiral galaxy over here, and what should be happening is that for the spiral galaxy, we should notice that these stars over here should be moving a lot slower than the ones in the middle. So the ones in the middle should be moving much faster than the ones at the end. The reason why is because these ones are closer to the center, so gravity must be acting the strongest, therefore causing them to move faster. But when astronomers actually looked at the data, they noticed that if you plot the graph of velocity versus distance from the center of the galaxy, that yes, it should have actually dropped down. The velocity should decrease as you get further out, but the velocity never decreased. It actually stayed the same. So the velocity of these ones is roughly the same as the velocity of these ones over here. So the velocity of the stars further out is much higher than expected. Therefore, there must be some extra mass somewhere which is causing this extra gravitational pull. We are going to call this dark matter. Physicists do not really understand it because dark matter does not give out any electromagnetic radiation. And that's it, everyone. That is everything in AQA Physics, GCSE Physics, Paper 2 in one video, guys. So hopefully that you can see that I've poured everything in my mind into this video. Hopefully it solves all your problems and hopefully it helps you in your educational journey. Good luck in the exams, everyone, and I'm sure that obviously the amount of effort that you put in will relate to the grade that you obtain at the end. Obviously the more effort you put in, the higher grade that you'll get at the end over here. And if you're still struggling in any of the concepts, you want me to walk you through certain things in detail, well, my YouTube channel, I've got bite-sized videos on every single topic, but obviously I go through it in a lot of depth. There's worked solutions. I take a bit more time explaining certain things rather than this just quick revision video here. So just make sure that you use all of it if you want to get the highest grade possible. Make sure that you like and subscribe to my channel and you keep it going, and good luck in your studies. Ciao, ciao, and goodbye. And if you're still struggling in GCSE Physics and want additional resources or private tuition, get in touch via my website.